welcome to Lambda Calculus, episode number 7. A little bit more. Yeah, episode number 7. So, what have we been up to? Select first. So we're doing the select first. Select first. What is the select first? So the select first is a lambda function. Well, select first is a function that out of two arguments would take the first one. And that's kind of I don't know, all of these functions have, I've been reading a bit, have implications. What did I find? Let's open up a new one. So select first function in Lambda Calculus. How's my CPU? Okay. Calculus is a function that takes an argument. How's my CPU? From two arguments. Yeah, I forgot. I was reading about this function. Well, that's not a combinator function. That's not a combinator function. Or it is. It's a K combinator. It's a K combinator, right? It's a K combinator. So it's kind of I don't know, it's like so deep, this thing. Combinators, right? The select first function is equivalent to the K combinator in combinatory logic. So here we have the definition of the K combinator. Lambda x, lambda y, and takes the x. That's basically our select first function. So the K combinator takes two arguments and returns the first one. And it's called a combinator. And it's kind of cool because when you look at the identity function itself, the first thing what we did, the identity, right? Maybe I could, should I open up like a new window? No, I'll just quit this one actually. The identity, right? Fnx lambda x and returns the x, right? I still haven't learned this. Identity fnx and returns an x. In some sense, in the sense, this is also a combinator, right? Like you can look at it, this is a, function that as its output returns its input. But then also on the next level, this is also the most basic combinator, and combinator is it's something that has no free variables, which means combinator is something that combines, right? And you could say, like, if I give you something and you return me the same thing what you gave me, it's the most simple, the most basic combination you could do. I think, when we say combination, we kind of make, let's say we have A, B, and C, and we have we do some sort of combination with what we have. But we usually, when we think of combinations, we have more than one thing. We have like 5 things, and you can say, okay, let's make a combination. So not 1, 2, 3, 4, 5, but for example, 2, 3, 1, 4, 5, or I don't know. So we're just making some sort of combination, or a combination of, numbers. So I guess, you don't think of it as, oh, if I have one thing and I return you one thing, that's the most basic combination. So the K combinator, I'm not sure if that would be the next one in the terms of, complexity. The K combinator, or would that be applied actually? That's also interesting. So we learned that the identity combinator is the most basic one, right? I give you something and you return that to me, so that would be the most basic combination one could do. But then in terms of complexity, what would be the next combinator? We had the self-apply and the apply functions. Are those combinators too? It seems so, because we didn't have any external or unbound or free. Free would be right. Free variables, right? Because we kind of had the self-application function, right? The self application one, right? The self application was the fn lambda f, and then we had ff, right? So we kind of had the same thing as the identity. I guess that would be the next thing. It's interesting when you look at things. So it's almost like you changed the lens. The first lens was you looking everything as a function, right? Which is something that can take an input and produce an output, right? Now, the combinator does the same thing, but it's almost like the input itself is not connected with the external world. The input is like bound already with the head. So like you could say, how do I, well, okay, you give it some input, but what does it do with it? It makes some kind of combination with it. Yeah, I was looking at the identity function. So here it's almost like the same. The self-apply is almost the same as the identity function, right? And if we just, we don't use the f, let's say use the same thing as the identity. Fn of, so lambda x, and just the x, right? And then the self-apply was just, we added one more x. So it's almost like the identity as its argument body had the argument applied to itself. And the self-apply was basically Fn of lambda x, lambda y. And then, what do we have then? xy. So in some sense, these could be also some types of combinators. That's kind of cool. You're spot on. So the identity combinator is the simplest combinator. It essentially does nothing but return its input. So what's next after the identity combinator? The next step up in complexity. The next step up in complexity would naturally involve combining multiple inputs or applying functions to themselves while still avoiding free variables so that they remain combinators. Now the self-application function. This thing will come actually, I saw this in the Y Combinator definition. In the body there are two of those in the Y. That will be very interesting to, finally understand what's the Y Combinator about. So this is a combinator since it has no free variables. It applies a function to itself. And this will be actually a building block to build the Y Combinator. Now, complexity, it introduces recursion-like behavior and is foundational in defining self-referential or fixed point behavior. And now we had the apply function. So this is also a combinator. It takes a function and an argument and applies the function, right? Lambda f, x, and fx. In some sense, it's almost like the self-apply, but it's just here, it applies it to itself. What I was confused at first, and it's still in the back of my mind, how can this thing be applying to itself if we only have one term in the head? How can this thing be applying to itself? Where does it get the power from? The power. Because I get this. I haven't found this online. You see, because every term here has a bound head, right? And the identity as well, it has a bound head. You're absolutely correct. Combinators comparing complexity. If we rank them by complexity, but that's if you want, we can explore the S combinator, which generalizes function application. Well, just one thing. One thing is confusing me a bit. So the identity has a term in the body and in the head of the expression. So an x and an x. And the apply has two terms in the body and lambda f and lambda a in the head. So there is some kind of symmetry between the number of the arguments in the body and in the heads. But with the self-apply, we have two arguments in the body and one in the head. How is that? How is that possible? Right. I mean, it's just something I haven't found online. I wonder what chat will say about this, but well, symmetry between arguments in the head and the body. So what? Identity head, it has one, and body, one use of that, right? Everything matches, one head, one body. Apply, head has two arguments. Create, was this thing showing or what? Probably because of the dark mode. Yeah, okay. I know it's late. Okay, so two arguments. Create lambda f and lambda x, and body has two terms, fx, right? That's what we had. I think this kind of question could arise. Everything matches again, two arguments, two uses. So why does the self-apply seem to break this? So at first glance, it feels like self-apply introduces a mismatch because head, one argument, and body, two uses of the argument, right? This is where the distinction between arguments and uses become crucial. So the head specifies how many arguments the function takes. In this case, the function takes exactly one argument. Oh, I saw that. The head specifies how many arguments the function takes, not how many times. The body defines what the function does with the argument. In this case, the argument x is applied to itself, resulting in two uses of x. Oh, I just got it. So lambda calculus imposes no restrictions on how many times an argument can be used in the body. A function can use its argument 0 times, as in 42. Use its argument once, use its argument multiple times. Yeah, okay. The head only defines how many arguments the function expects, not how it uses them. Yeah, or you could say not how many times it uses them, because a function takes a single argument. I was kind of thinking in the body there should be only one as well. That was a mistake on my part. Yeah, fascinating. Think of self-apply as asking a single argument to loop back and interact with itself. The symmetry you're observing in identity and apply reflects simpler direct relationship between the arguments and the body, while self-apply introduces a self-referential pattern. Yes. Your original assumption, while intuitive, doesn't quite align with how lambda calculus works, right? So that might actually happen because you learn a function in lambda calculus, right? But it's not just with lambda calculus, because the most basic function that you could think of takes a single argument and outputs a result. You could say, okay, it takes a single argument, but maybe twice. Multiple times, not at all. You see this? It takes it once, but it uses it. Okay, it takes a single argument and it uses it twice. Which maybe sounds confusing, right? But it uses the same thing twice on itself, self-apply. Which it's fascinating. I don't know, it's just sounds so deep. Because this is basically like the entire computation, rests on this. Because almost like the self-apply is the most simplest computation like function. I don't know. I mean, I don't know math. I don't know math. So, but it's just a function's body isn't constrained to match the number. Yeah, freedom, single comparison. Okay. So now we're doing the self-apply. We were doing the self-apply argument. Okay, so now we're doing argument selection and argument pairing functions, which are, pretty deep stuff also. Pretty deep stuff. Let's check what the chat says about it. So now comes pretty deep stuff, right? The argument selection function, which takes the first argument and then the second. This has all kinds of implications in computation theory. Yeah, I'm sure. The argument selection functions, the K combinator, and its counterpart are fundamental in computation theory. The argument selection function K combinator takes two arguments, always returns the first, ignoring the second. And the definition, it's not hard. Like from all that we saw before, this kind of comes. I think when you first see it, that's why sometimes when people teach, lambda, they show like this, the bools. I take the first, I take the second, and I take the first. From the first and the second, I take the first, which is a kind of a conditional, right? Why K is profound. Selective attention. K introduces the ability to choose an argument explicitly, laying the foundation for Boolean logic, decision-making structures, if then else. Control flow, right? And so we are going to have control flow now. Gain ability to manipulate. What are you planning to use your knowledge of lambda calculus for? Like, what's the purpose? Oh, hi, hello, Dapster. What's the purpose? Well, the purpose is first of all like to study um, computation. I'm kind of interested about that, but also to better understand functional programming languages. And because you can see it, the way that it moves. I'm just going really slow with it, and I don't know, this is so interesting, like learning about combinators and stuff. And yeah, and it's like yeah, I don't know, it's just so deep and profound, and it feels like whatever you learn with this, you can see it, that it helps you with everything else. It's almost like you can feel it, because you learn all the, like, even now, okay, in last like 2 weeks that I'm doing this, and then I went to read some Haskell code, or even just read and it just makes a little more sense, everything. It's not that I know this or that, it's almost like there is more light. Like before it was more dark, and then you're trying to find things in the dark. But when you learn this, it just brings more light to whatever you're doing, and then it's nicer, and this is the basic actually of computation. This is so church was the teacher, or like the doctoral advisor from Turing. So they both were, this is like, and also when you read the functional code, the way, I just finished my CS class with a perfect score. Oh, congratulations. Chinese history. Then I can spend all my time working on my Lisp. And also it's all Lisp, like all that we're doing here in the apply, Lisp is based on this. It's just Lisp. Lisp has no, well, what do you call it? It's not like static or like something. I'm not sure how you say it, because Lisp is based on Lambda Calculus. And when you learn this, like, it's, yeah, anyway, I'll just move my hands now, trying to explain it. And also, from one thing, I think this is really fun, and the purpose itself is just intellectual, so it's not like I will do this to build something, because I don't know, it's just fun also, and so deep. Yeah, anyway. Okay, why this is deep? Enable abstraction service. And it's interesting, you can build everything from these, functions. What's kind of interesting is these combinators, and I don't have any idea about that, but the combinators are like thing in itself. I've read that combinators are like one more level of, it's like you could build a computer out of combinators, which take no external things, but they could compute anything. And from one sense, the identity is a combinator as well as a simple function. And the Boolean also is a combinator that takes the first or the second, what you provide. So it's like, yeah, I don't know, it's cool. The implications. Well, good luck with your working on my Chinese history. Yeah, good luck with your final paper. The implications of these simple selectors. Yeah, enable abstraction. Where was I? Selecting the first of the two arguments, consider the function def select first. So also now he's kind of using this def here, and the def here is not really something that means in Lambda Calculus. This is just like pseudocode. So he's using that to name the function definitions with a name, to give them a name. So right, so let's do this again. Let's do this again. So we're going to have a val select first, and select first will be a lambda x and lambda y. Well, no, actually let's call it fst is the first, and lambda snd, and it will select the first, right? And val select second, select, I wrote select, cell first. Wait, I'll do it again. Val s first, select first, select first, fn fst, fn snd, and this will be fst, and val select second, fn fst again, fn snd second. So now we have a select first and select second, which are the bools. Consider the function. Okay, so the function has a bound variable first, which is this. When it says bound, it's here, it's in the head. In the head it is bound. It's like in the head it's bound, and here it's also in the body, right? And the body second first. The function has a bound, well, it's, yeah, but the function has a bound head here, and the body is not this, right? The body is this. So the body itself has another function. When applied to an argument, it returns a new function, which then applied to another argument returns the first. So this thing is describing when applied to an argument, it returns a new function. So when this thing is applied to an argument, it returns a function that returns the first argument. So this kind of way of, talking, and I've noticed that with, functional programmers, or when they describe things, a lot of it has to, it's like a way of, speaking. After you read that a lot, or like you hear that kind of a talk, it kind of is going inside, outside, or the thing from the outside, and then you almost like split it into the thing, and its head has this, and then this, and this. It's kind of like zoom in and then zoom out, and then zoom in and then zoom out. It's almost like it's very fractal way of talking, actually. So even when you describe a program or sorts, it's like you go inside, you cut it in half, and then you describe the thing, and then you go inside. So it's almost very hand-like, I think, because we have two hands, and we can go inside, and then we have, again, two hands. I can grab this and this. In some sense, yeah, I don't know with hands. But when applied to an argument, it returns a new function, right? Which then applied to another returns the first. So it's like that. And when you read that at first, it's really hard. I don't know. I mean, it was hard for me. You just don't get it. You just read like one sentence and you're like, I don't get it. I'm not sure how is it when you, when you do like memory, and because that actually refers to, you know, places. When you go there and you go back and then you go there and then you go back, then you return it there and stuff like that. I think that's kind of maybe a bit, you know, different than, well, different in a different kind of way than here. So select first, identity apply. So now he is actually, they are select first, identity apply. And you basically don't need this parentheses, but he's putting them here so that you can actually see. So the function application goes from left to right. So you first group the first thing here, and then that thing itself is being applied to this thing here. So you basically wouldn't need these parentheses, right? Because it works like this, FAA, right? But he's actually doing it like FAA, right? But you don't need to put them. But I think he's just doing this so that you can, you know, see actually how the application itself, you know, how it works. Select first, identity apply. And also the thing which was, so when do you actually expand on the name and substitute for the definition? So here actually he puts the select first, and he's going to apply to identity and to apply. So he's going to give it two things to choose from. And the select first is going to pick the first one. It should pick this. It should pick the identity, not the apply. But now what does he do? He expands on the select first, right? So if I, what did I do? What did I do? Okay. Select code lambda. What did I do? What did I do? What did I do? So let's say we have select first and identity, right? And apply. Yes. Okay, I'll do it just like he did actually. Select first, identity, apply. And now he's gonna expand on the select first. And now we have to know. You see, that's why it's good to do this with pen and paper and stuff. You practice the substitutions for the names, and then you from the name, and then you practice how it all connects. So select first is going to be a function. Let's do it. Are we going to do it like this? Maybe let's do it like this. FA. Oh, first. No. Let's do it like I said. First. Or let's do it like this. Let's try like this, then with dots. But dots is like really short. FST. I think this is how you would do it in Haskell. Maybe we could do it in Haskell actually. FST, SND, FST, right? And identity, apply, right? Identity apply. I think I need one more here actually. FST, SND, FST, identity apply. So FST is a function that will take an argument and output a second function that will discard. Yeah, you see, that will take a second argument. No, that will just output the first one. It will not even take the second one. It's just, I guess the confusing part is because it's called second. What does it do? It just returns the first. It doesn't even take the second, right? I wonder what you would think. Is the bool something that takes the two things and returns the first? Or it does not even, it just returns the first? It discards. the second. But then what does it mean to discard? Like I take it and then I throw it away. Like what is happening here, right? So I think I should actually substitute. So we have the first and the first. So identity now will go inside of instead of the first, and then we will remove the head. So I'm going to have the second and identity.